All right, so you got that homework tonight, W4.2, and it's based on this notes page 5. It's also based on your previous knowledge of simple geometry. You already know how to deal with vectors. Here's a reminder. So vectors, we have done the following two cases. When the angle is 0 degrees, so you have them set up like this, and we have done when the angle is 180 degrees, which looks something like this. And so, of course, in this 0-degree case, you ended up adding the magnitudes. In the 180 case, you ended up subtracting the magnitudes. That stuff all worked well and good. Now we are going to the 90-degree case. So the 90-degree case is actually a pretty easy case mathematically. As before, these notes are identical in intent and probably more or less in language to what we've done before. When multiple vectors are combined, they create a result, which we call the resultant. The resultant is also a vector. It's also an arrow. It requires an arrowhead. It must be drawn with a ruler, straight. All right, the rules are the same. Vectors can be translated. So if this were a vector, you can move it around wherever you want to move it. You cannot change its length, cannot change its direction. So it's a certain length to the right up here on the board. That's what it must stay. The reason we translate, though, is so that this vector and perhaps this vector, through translation, can be made head to tail. Now they're head to tail. This also is head to tail. So it doesn't matter which way you orient them head to tail, or which order you go in to orient them, but it must be head to tail. Once they are head to tail, you will see that there is an exposed tail. That's this one and the green one. Circle it. If you follow the green arrow, it connects to the red arrow. Follow the red arrow, it connects to the head. That is an exposed head. Put an X on that exposed head. The resultant then is drawn directly from the circle to the X. It points toward the X. That is your resultant. Here's another example on the side. Okay? That's it. Same as before, except now we're going to deal with the 90-degree case. Mathematically, this is very easy. Here we go. Here is a little bit of an aside, but it's going to become very relevant this unit, Unit 4. All vector quantities in Regents physics come in 3 flavors. 3 flavors. The flavors are X, or what we call the X component, Y, what we call the Y component, and the combination of the two, which we call the resultant. Component you see is underlined. That just means a part of a greater whole. The components are the individual vectors that combine to form the resultant. Very important note here, which won't seem that important yet, but it will become important. If the component is not mentioned, it implies the resultant. You may say, what are you talking about? You'll see in a moment. Okay, let's look at an example here. These 2 examples should get you on point for the homework. Question 8. A ball has not just a velocity, by the way, you know this is a velocity because it says meters per second, but a horizontal velocity, that's the X component, of 30 meters per second. So if we come over here and put our given units, you could put velocity in the X direction. Horizontal is the X direction for us. It will be 30 meters per second. Now, for the moment, I don't mind, it says rightward. I don't mind you putting a little rightward arrow. That's fine. Another thing you could do, which would be appropriate, is you could define rightward to be positive. Put a little plus over here, fine. But the arrow is going to be of more help here when we're working in 2 dimensions. That means X and Y. We also have a vertical velocity of 40 meters per second, and this one is downward. So the velocity in the Y direction is 40 meters per second, and this one is downward. Now, this is a different dimension. Right, left is positive, negative. Up, down. Well, here we can call down positive. Again, we're not really going to use that when we're doing 2-dimension right now. There are times we will, but not just yet. The arrows will be more helpful to us at the moment. And finally, determine the magnitude of the ball's velocity. All they say here is the ball's velocity. Notice, now that comment comes into play. Did it say X or horizontal? It did not. Did it say Y or vertical? It did not. Since it said neither of the above, it actually is implied, or it is saying, the resultant. So really what we are looking for is the resultant velocity, and they're actually looking for the magnitude of it, which just means how much. So how do we draw this? Very simple. 30 meters per second to the right. There's your velocity equals 30 in the x direction. Then we have 40 meters per second down. Well, why not make them head to tail straight away? That's what I'm going to do. 40 meters per second, straight down. Here's my velocity, 40. I tried to make that one a little longer than the 30. I may have failed in that regard. Maybe I'll shorten up the 30 just a little bit. And then finally, find the resultant. Well, that's actually very easy at this point. Find the exposed tail, circle it, follow the blue arrow, follow the red arrow. There's the exposed head, exit, and draw your resultant directly from the circle to the X. Put an arrowhead on it. There is your resultant velocity. There are two different ways you can know the resultant velocity. In this case, the easy way, which we call the finesse method, is to recognize that this is a 3, 4, 5 triangle. Conveniently, it then would be a 30, 40, 50. So we know the resultant velocity's magnitude is 50 meters per second. If we don't remember the finesse method, we always have the brute force method, which is, in this case, Pythagorean's theorem. A squared plus b squared equals c squared. Truthfully, this is more appropriate to write as vx squared plus vy squared equals vr squared, but I don't particularly care. When you substitute, make sure you put your parentheses, 30. If you have a list of givens, you don't need the units. But if you don't have a list of givens, you better have those units over here. 30 meters per second squared plus 40 meters per second squared equals the resultant velocity squared, or c squared, however you want to write it. Solve for c and you will get 50 meters per second. Okay. By the way, a little note that will come into play later on. Within any resultant problem, the components and resultant will have to have the same units. They're all velocities, or they're all accelerations, or they're all displacements. All right, let's look at this plane problem. A plane is attempting to land in a strong westward pushing crosswind. Okay, they're telling us something. A westward pushing crosswind. If the plane's engines are directing it at 150 meters per second northward. So, when you're first putting your givens together, you sort of have to feel out what's happening. So you could say like velocity of the planes, let's say engines, I'll put an E for engines, is 150 meters per second northward. I'll put a little n over here. These two-dimensional problems, sure, we can call north positive, but we're going to need to draw an arrow for this. And its velocity is 200 meters per second. Its velocity is 200 meters per second northwest. Oh, wait a minute. Its velocity. What is that? Does it say X or horizontal? Nope. Does it say Y or vertical? Nope. So what's it talking about? Boom! It's talking about the resultant. The component is not mentioned, therefore it is talking about the resultant. So actually, the resultant velocity is 200 meters per second. This one is northwest. And the question says, what is the magnitude of the crosswind? Well, they said up here the crosswind is westward. So the velocity of the wind, we don't know, but we do know it's westward. Now, at this point, if you try to visualize the answer, you might run into trouble. Draw your arrows. If you draw your arrows, it makes your life much easier. Let's call toward the top of the page north. And if that's the case, you know that this arrow will be up toward the top. The resultant arrow will be northwest, which is up and to the left. And the wind arrow will be left or west. right? You never eat soggy worms, or however you remember it. I remember it as wheat. Anyway, knowing that, you can now start to piece together this picture. Keep in mind what we have here. The engine is a component. The wind is a component. The resultant, what I have up here in purple, that is the result of circle and X. So how you may want to draw this is, let's put our 150 this way, northward. That's our V equals 150. We know that there's a westward, even though we don't know how much it is. Let's just sketch it in there, head to tail. Put it here. Here's your westward. We don't know how much it is. We also know that there's a resultant. Well, where does the resultant go? Circle the start, X the finish. Directly from the start to the finish, and that velocity resultant should be northwest. It is, and it's worth 200. Great. Can we find that westward component? Well, actually, it's quite easy. It is again Pythagorean theorem. Here we can say velocity northward squared plus velocity westward squared equals the resultant squared. You also, again, can write a squared plus b squared equals c squared. That is perfectly fine. So this is 150. We already have our units in our given, so I'll leave them out. Squared plus VW we don't know. I don't even know if you need to write your parentheses there. That's the one we don't know. Velocity westward squared equals 200 squared. Solve for velocity westward, and you will have the square root of 200 squared minus 150 squared. And have the answer written for us over here. I trust that I have done this properly, and that's going to be about 132 meters per second northwest. Or sorry, west, my mistake. Sorry. 130, this is the westward, 132 meters per second west. So now we can come write this in over here, 132 west. Great. We have one more piece left for this, and here it is. The line style's good. What is the angle between the north and northwest vectors? North is our red arrow. Northwest is our purple arrow. The angle between them is right here. Now, more than one way to skin this cat. You could use sine, cosine, or tangent. It doesn't matter. Personally, I would like to use what the problem gave me. They gave me the north and they gave me the northwest. Those numbers I can trust because I did not calculate them, they were given to me. And so with that in mind, the north is adjacent to the angle. The northwest is the hypotenuse. So we have adjacent and we have hypotenuse. Well, that's cosine. The cosine of theta equals adjacent over hypotenuse. You could also have written this, the cosine of theta equals the velocity northward over the velocity resultant, or the velocity northwest, however you want to call it, or the velocity engine, doesn't matter. Anyway, when you're solving for the angle, that's our goal. Let me write this down here. When you're solving for the angle, you must undo the cosine. The way you undo cosine is with inverse cosine. So if you inverse cosine both sides here, I'll write it out fully for you, just in case you haven't seen this in a while. Inverse cosine of theta equals inverse cosine of adjacent over hypotenuse. Now, inverse cosine undoes cosine, so these two go away. And so now we're actually left with theta equals inverse cosine of adjacent was 150, hypotenuse was 200, and of course do the math, and this should come out to what we got over here, 41.4 degrees. That's how you do it. So this is all basic geometry that you have done before. As with all things we do, take the time to set nice givens. And what we will start to add to our repertoire, which we've been doing, is make a nice sketch. So good set of givens and a nice sketch. You will be amazed. This will take you so far in this course. Good givens, good sketch. Don't get stressed about the math. Now, let's pull up the homework. Here it is. And just let me give you a couple of tips here. Total distance, number one, you don't need my help. Number two, so this is W4.2. What is the magnitude and direction of Mr. Ross's displacement from his start? So if you set up your givens with units, what you have here is 12 yards forward. So we can have like displacement 1 is 12 yards forward. And then displacement 2 is 5 yards to the right. And the question down here is find the displacement. And it doesn't say forward and it doesn't say right. That must mean it is the resultant displacement. Now, if you just choose which way you want to be forward and right, this is very easy. Like forward, I'll choose this way. And right, well, if I'm going that way, then right becomes this way. You didn't have to make that choice, but that's what I picked. And so the sketch becomes forward, and then make it head to tail. Right. There it is. Easy. Label it, circle, X, find the resultant, and then it says find the angle. Now, if you look at the key, the angle I chose was right of forward. Ooh, that was interesting. The angle I chose was right of forward. See that down here? Right of forward. So if this is forward, this one, and this is right, then right of forward is going to be the angle that you end up getting over here. Follow that the same way we did the last one in the notes. Here's another one with the airplane. Very similar to what we did in the notes, except this one's easier because I gave you the flying, this is like the engine, and I gave you the crosswind, and I asked you for the result. So this one's actually easier than the one we just did in the notes. Finally, down here, please do not mess around with questions 4, 5, and 6. You must follow the process explained in the notes. Do the 2-step process explained in notes 5 or your answer is junk. Please do this one correctly. Do not mess with my emotions. All right.